Hello, this is Jake Gunther, and we are going to talk in this video about the geometric series. In a previous video, we learned about integrating an exponential function. In this video, we're going to learn about summing an exponential function. And this is what we're talking about here. So these are formulas that should be memorized, and because we will use these so often that it's worth memorizing these. There's two different cases to consider. One is a case where the limits are finite. So that's the first case we're looking at here, where m and n are finite numbers, not infinity. And there's even within this situation, there are two different cases to consider. One case is when a, the value of a, which could be any complex number, when a is equal to 1, whenever you exponentiate 1, you still get 1, and so that's a special case. In that case, we're basically adding 1 together a bunch of times. How many times? Well, it turns out if you count all of the terms, the number of times that we're adding 1 together, it turns out to be n minus m. So when a is 1, then we just get n minus m, which is the number of terms. For all other cases, for a not equal to 1, we get this formula that is shown here. And we'll derive that and see where that comes from. The other case is when one of the limits, usually it's the upper limit, becomes infinite. And in that case, we have this additional requirement that the magnitude of a, remember a can be a complex number, the magnitude of a has to be less than 1. And in that, boy, I can see that I need to rewrite this slide. What I'm talking about here is the sum from n going from m to infinity, a to the n is equal to this formula. And then here we have n going from 0 to infinity, a to the n is equal to this ratio here. So with that little correction, these formulas are correct, and we'll take a look at this in the following pages. Probably the two most common cases that you'll encounter are this case here, where a is not equal to 1, so finite limits, a not equal to 1. And then this other case is very common, where you have the upper limit being infinity, the lower limit being 0. And so this is the other very common case. But again, that holds only if the magnitude of a is less than 1. So let's jump into this and take a look at these different cases. First of all, let's take a look at the situation where we have finite limits and a is equal to 1. So here we have that sum expanded out a bunch of different times, all the terms written out explicitly with dot, dot, dot. And if you just count the number of terms, it turns out to be n minus m. To see that that's the case, we'll look at a few examples here. First of all, let's suppose the lower limit is 0 and then n is equal to 1. So in that case, if we plug those numbers into this formula, we have the upper limit will be n, which is 1, minus 1, which is 0. The lower limit is 0. So we actually have one term. We're summing from 0 to 0, so that's one term. And we're summing 1, and so that turns out to be 1. And it turns out to be n, the value of n minus m as well. Let's take a look at another example. And here what we'll do is we'll say, well, let's let n equal 2. So if we substitute these limits into the sum, we'll have the sum from 0 to 1 of 1. So we're adding 1 together twice, the n equals 0 term and the n equal 1 term. This is the n equals 0 term, and this is the n equal 1 term. So 1 plus 1 is 2. That turns also out to be the value of n minus m. Let's look at another example. Let's just try something very random. Let's sum from 20 up to n minus 1, which would be 22. And so here's the terms. This is the 20th term, this is term 21, and this is term n equal 22. 1 plus 1 plus 1, well, that's 3, and that also turns out to be the value of n minus m. So hopefully by looking at a few of these examples, we trust that this formula for the case a equal to 1. Now let's look at the case where we have finite limits and the value of a is not equal to 1. I'm going to cover up part of this so that we can reveal it as we go. So what we've done here is basically just expand the sum, writing out the terms, as many as we care to write. And now thinking about, well, how can we derive a formula for this? Let's take that same sum and we will multiply each term in that sum by this value of a. Notice that each term in the first sum differs from the previous one just by 1 power of a. And so what we've done here in this second sum was we've just moved all of those terms over 1 by raising the power on each one by 1. And I've written this in such a way that like terms lie beneath each other here. And what I want to do is subtract. So when we subtract the first sum, the second sum from the first sum, we'll get a to the m. That will come down because there's nothing to subtract it. But all of these other terms will cancel, and then we'll have the last term coming down. And so notice that we can factor out this summation. The summation is the same. So if we factor that out, we'll have left 1 minus a, 1 in the first term, a in the second term. And then if we just divide both sides of this expression by the quantity 1 minus a, we have derived that geometric series formula that you see here. So it's pretty straightforward to perform that derivation. You can also see why we are very cautious about saying things like a not equal to 1, because if a was equal to 1, we might think something very bad is happening in this expression, because we would have 1 minus 1 in the denominator. But we already know that it's not appropriate to use this formula when a is equal to 1. We'll just go back and use the other formula, which gives us n minus m. Okay, so we've safely derived this formula. Now let's move on and take a look and see what happens when we let the upper limit tend toward infinity. Let's just look at the terms in that case. Let's suppose that a is a complex number, and let's write it in polar form, where r is the magnitude of a and omega is the angle of a. And then if we just look at the behavior of these terms, what happens as n goes to infinity? Well, if the radius, or the magnitude of a, is less than 1, then this tends to decay as n goes to infinity. If the radius is equal to 1, then this function just oscillates, the sequence just oscillates. And if the magnitude is greater than 1, then it will tend to grow as n goes to infinity. So that if we take the limit as n goes to infinity of these sequences, when r is less than 1, we get 0 in the limit. And we just don't want to deal with what happens in the other cases. So let's assume we have the magnitude of a less than 1, and let that upper limit go off to infinity. Well, what we'll do is we'll just substitute in the upper, or this formula that we derived a few minutes ago, and let n go off to infinity. Well, we know that the value of a raised to the n decays to 0 if the magnitude of a is less than 1. And so all that we'll be left with in that case is this expression here, which is one of the formulas that we wanted to derive. So that's the sum of a to the n, starting at some finite value, which could be positive or negative or 0, and going up to an infinite upper limit. Finally, if we just let m be 0, we get this special case here. And because that's used so often, it's worth pointing out here and remembering. So those are the proofs. And now the next thing I'd like to do is use this to actually perform some sums. So the first sum that we'll do, well, maybe we'll just do one sum here. Looks like we're just going to do one summation. Let's perform this sum. We'll go from 0 to n minus 1 of e to the minus j 2 pi fn. So here we're thinking that a is taking the value e to the minus j 2 pi f. And we can substitute this into the previous expressions. So we have finite limits, and so we can use the formula for finite limits, which is a raised to the lower limit, so a to the 0, that's 1. Then we have minus or a raised to the upper limit plus 1. And let's just go back and take a quick look at that formula. This is something worth noting that I should have pointed out before. Notice that when all is said and done, the form for the answer for the sum is we get a raised to the lower limit, and then we have a raised to the upper limit plus 1. So this is the upper limit is n minus 1, but the form of the answer, we have that upper limit plus 1. So if we apply that here we have an upper limit of n minus 1. So here I'll have e to the minus j 2 pi fn. And then in the denominator, I'll have 1 minus a, which is e to the minus j 2 pi f. We could stop here. This is a correct answer, but it would be nice, once again, if we could express this in the form of a sinc function. To do that, I'd like to step aside and do another example problem here. Let's work this problem. N going from m up to n minus 1, e to the a n. Using our formula from before, we have e to the a lower limit, m, minus e to the a upper limit, plus 1, n, over 1 minus e to the a. All right, now what I would like to do is, using a trick like the one we saw previously when we were doing integrals of exponential functions, I'd like to factor out the difference of the exponent. So we'll have e n minus m over 2 minus e to the minus a n minus m over 2. We'll do the same thing in the denominator. So I'll have e to the a over 2 minus e to the minus a over 2. And then we'll have e to the minus a over 2, and then e to the n plus m over 2. And we better check our work here just to make sure we have done this correctly. I think I'm going to change this and put pluses here on both of these terms. Let's see what happens when we multiply this back together. So let's look at this first term. So e to the a n over 2 combines with e to the a n over 2 here, giving e to the a n on this term. And then we can see that the minus m over 2 and the plus m over 2 here cancel. So let's just write this out. So this would give me e to the a n. Then I'll have minus. If we multiply these exponentials together, we'll add the exponents. So we can see that the n's cancel and the m's add. So here I have e to the a m in this term. Let's look at the denominator now, and then we'll compare with what we should have. So here I'll have e to the a, and then when I multiply these others together, I'll have 1. Now what we should have obtained is something that looks like this. And you can see that these actually are equivalent. They look a little different, but they're equivalent, because if I multiply top and bottom by -1 and rearrange the terms, I'll have e to the am minus e to the an, and then 1 minus e to the a, which is the same. So let's see if we can remember what we've done. What we'll do if we want to write down the answer to this sum is we can say this is e to the a, the difference over 2 of the limits, minus e to the minus a, difference over 2 of the limits, and then here's e to the a, average of the limits. Same thing in the denominator, or similar sort of thing in the denominator. Let's apply that here on this summation. When we do, we will have, let's see, I'm going to slide this in here. I'll have e to the minus j 2 pi f, and then I'm going to have the difference of the limits, so this would be n over 2 minus e, now I'll have plus j 2 pi f n over 2, and then I'll have e to the a, e to the minus j 2 pi f and 1/2, that's this exponent, e to the minus j, or plus j 2 pi f and 1/2. This whole thing times an exponential, e to the minus j 2 pi f. Then we're going to take the average of the limits. So I'll take n minus 1 plus 1, that's n, plus 0, n over 2. And then here I have e to the minus j 2 pi f 1/2. Okay, now let's simplify this. I want to find something that looks like a sinc function. So I need to have this exponential with the positive exponent first, both in the numerator and in the denominator. So multiplying top and bottom by -1 allows me to write e to the j. The 2's are going to cancel, so I'll have pi fn minus e to the minus j pi fn. And then in the denominator, the same sort of thing happens. I'll have e j pi f minus e to the minus j pi f. And then I'm going to multiply by 2j and 2j. I'll need that to convert the numerator into a sinc function and then the denominator into a sinc function. But let's finish writing this out. We'll have let's see, the 2's will cancel, pi f, and then I have n minus 1 if I combine the denominator exponent with the numerator. So finally, writing this out, I'll have sine of pi fn divided by sine of pi f e to the minus j pi f n minus 1. So this is a sum. This sum here shows up very often in applications, often enough that it's useful to recognize it, and we see that it's not quite a sinc function. This is a function that if we did not have a sign in the denominator, it would just be a sinc function times a complex exponential. It turns out that this is a function that shows up often in digital signal processing, and this is a periodic sinc function, or at least that's what I'm going to call it. And let's take a look and see what that actually looks like. So the subplot on the top shows a linear amplitude periodic sinc function. You can see why it's called a periodic sinc function is because it has it repeats, and in fact the period is equal to 1. You can see that that is the case here in this plot. The amplitude is n. Remember, here's the function that's being plotted. I removed the exponential function, the complex exponential, and we're just looking then at the real value, or the sine pi fn over sine pi f. I plotted this for the case when n is equal to 9, and it's useful to know how that number n, or how the plot would change if the number n changes. And let me just note that if we count the number of zero crossings in one period, we have 1, 2, 3, 4, 5, 6, 7, 8. In general, you'll have n minus 1 zero crossings in each period. Let's count the number of peaks that appear in one period. So here's one peak, or let's call them extremities. 1, 2, 3, 4, 5, 6, 7, 8. So once again, n minus 1 extremities of this function in one period. Down below, we're again looking at the log magnitude of this function. And so you can see that in any period there are 1, 2, 3, 4, 5, 6, 7, 8 nulls, n minus 1 nulls in any period. So this is a periodic sinc function. It appears a lot in digital signal processing, so we'll encounter this again. The important thing is to be able to begin with a summation of a complex exponential function and write it down in final form that this is a periodic sinc function. The other thing that I'd like you to be able to do is make a plot of that kind of a function in MATLAB. So let's talk about that for just a minute, because there's a few little tricks that occur. We saw in the previous video that MATLAB has this sinc function built in, but unfortunately that's not going to help us in this case. But what will help us is if we take a look at the internals of and see how the MathWorks decided to write their code for the sinc function. And I've reproduced the body of that right here. They look through the input, they scan the input and look for any points where x is equal to 0, because that's a special case. We need to avoid dividing by 0, otherwise MATLAB could throw a warning or do something bad. So to avoid that, what we do is we first look for any points where x is equal to 0, and then we set the input at those values. So this find function returns the indexes into this array called I, and then we use that index array to set to 1 all of those values of x that would produce a zero, a divide by zero in the sinc function. And there's nothing special about the value of 1. We could have set it to almost anything as long as it's not 0. And then we go ahead and evaluate the sinc function. And then finally we correct those values that were improperly computed here by setting the outputs at the indexes where we know we should get 1, where the function should have a value 1. We just set the outputs at those indexes to 1. So now let's think about how would we code this function, the sine pi fn over pi f, sine pi f. How would we code that function? Well, we can take inspiration from the way the MathWorks coded their function. And what we need to do is avoid dividing by 0. So basically, in the denominator, we get 0 anytime x is equal to an integer. And so what I've done is written some new code here where we look through the input array for all those points where x takes on an integer value. And I find the integer values using the modulo function. So if you take any real number modulo 1, if that modulo returns 0, then that input value must have been an integer. And after that, we just follow the same procedure as before. And but instead of evaluating the sinc function, we evaluate this periodic sinc function. Now we can use that to make a plot. Here's a piece of MATLAB code that will then plot this function. Only the first 3 lines are really important here. So I set the value of capital N to 9. I evaluate at a whole bunch of frequencies between -1 and 3. And then I call this function sinc periodic, the one we just wrote, to capture the values of the function. The rest of this plotting is just plotting code. If you run that code, you get a plot that looks about like this. And that's all I wanted to say about plotting. The last part of this is a little assignment where I ask you to perform the summations and to put your answers in the form of sinc functions, and then to make linear and logarithmic plots in MATLAB. So here's the general form of the sum, and I give you 3 different intervals. One is a symmetric interval, one is a non-symmetric interval. That's like the one that we did, that we worked together in this video. And then the third one is a union of 2 disjoint intervals. And so once again, that should produce for you a set of 2 sinc functions.